All right, quality of service. Okay, module title is quality of service. Objective is explaining how networking devices implement quality of service. Yeah. So network transmission quality, explain how network transmission characteristic impact quality. Yeah. So we have a topic under traffic characteristic. Yeah. Describe minimum requirement for our data like voice, video, and also some for traffic data. So queuing algorithm, describe the queuing algorithm used by networking devices. Yeah. And model of quality of service, describe the difference among them. Yeah. And quality of service implementation techniques, how quality of service use mechanism to ensure the transmission quality. Yeah, so that's very important things. Yeah. So for your information, this chapter we don't have much test actually. We don't have some. Yeah, we don't have that kind of like exercise a lot of on packet tracer. We don't have that on this. Okay, just information on theory is very important. Yeah. And also for finals, yeah, final there will be some quite interesting, yeah, because this is more on related to theory. Okay, quality of service, basically network transmission quality, yeah. Okay, so this video I'll try to play the video. All right, so there's give me 1 second, so I need to pause.
QoS, what is it and why is it needed? QoS, or quality of service, allows us to prioritize certain types of traffic over others. Different types of traffic place different demands on the network. Video traffic and voice traffic require greater resources from the network. They require more bandwidth to achieve the type of quality that is needed in a phone call or streaming video. Financial transactions are greater needs. Then let's say a web page or regular data traffic like sending an email. In this diagram, we're given a general concept that works. Packets buffer queues have been established: a high priority queue, medium priority queue, and a low priority queue. Voice over IP traffic in the high priority queue is given a higher priority, so more of those packets are allowed to be. Financial transactions, which are time sensitive, are also given a greater priority, so more of those are allowed as well. And then last, in the lower queue. When do we need QoS? We need this could be points where you have an links, let's say many computers or many users all having to go up a single uplink or a single wire. You can have situations where there's a speed mismatch. You're going from a faster link to a slower link. As you cross from or from the WAN to the LAN across a gateway route. Access they come or we experience packet loss. Now, if you're trying to stream a voice call or audio stream and you're experiencing excessive jitter or variations, the playout delay buffer can't tolerate it, and packets are dropped due to that excessive jitter. Now, too many packets being dropped results in your call dropping out. Packets are processed or forwarded because they're in the high priority queue and it's been configured for 0 packet lengths. So you still have, let's say, variations in delay and you can have jitter, but an audio stream is able to make up for that, and a playout delay buffer can send out a constant stream of audio information, resulting in a call that experiences 0 drop off.
All right.
Greater resources from the.
Okay. All right. So that's explaining, yeah, on quality of service and why it is needed. It's very important, yeah. Okay, network transmission quality. Okay, from the video that we can see that, yeah. Prioritizing traffic, that's very important. Yeah, when traffic volume is greater, yeah, greater than what can be transported across the network, devices queue, which is they will hold. So the packet in memory until resources become available to transmit them, right? So queuing packet causes a delay because a new packet cannot be transmitted until previous packet have been processed. Right. If the number of packets to be queued continue to increase, yeah, so the memory within the device fill up and packets are dropped. Okay, so that's the can say the algorithms, yeah, for this, yeah. So one quality of service technique that can help with this problem is to classify data into multiple QoS, yeah, as shown in the figure. All right, this one. Okay, they try to aggregate according to the time of that. All right. So bandwidth, congestion, delay, and jitter. So network bandwidth is measured in the number of bits, yeah, that can be transmitted in a single second or bit per second. Network congestion causes a delay, of course, yeah, and interface experiences congestion when it is presented with more traffic than it can handle. Network congestion points are ideal candidates for quality of service mechanism. The typical congestion point are first aggregations, speed mismatch, and also LAN to 1. Yeah. Okay. So that's a typical congestion point. Okay, delay or latency refer to the times it takes for a packet to travel from source to destination. Fixed delay is the amount of time specific process takes, yeah, such as how long it takes to place a bit on the transmission media. Okay, variable delay takes unspecified amount of time and is affected by factors such as how much traffic is being processed. Jitter is a variation of delay, yeah, of received packet, yeah, the variation of delay, yeah, a lot of them. So delay, can you see here, we have a code delay, packetization delay, queuing delay, serialization delay, propagation delay, and the jitter delay. Okay, so 6 altogether, the delays. Packet loss. Without a quality of service mechanism, time-sensitive packet such as real-time video and voice are dropped with the same frequency as data that is not time-sensitive. When a router receives a real-time protocol or RTP, digital audio stream, for VoIP or for voice over IP, it compensates for the jitter that is encountered using a playout delay buffer. The playout delay buffer the playout delay buffer buffers this packet. Okay, they will buffers all this packet, then play them out in a steady stream. All right, this is how they works. Okay, all right. If the jitter is so large that it causes a packet to be received out of the range of the play of buffer, the out of range packet are discarded and dropouts are heard in the audio. Okay, so we heard some missing of the packet. For losses as small as one packet, the digital signal processing, okay, DSP interpolates what it thinks the audio should be, and no problem is auditable to the user. Okay, because small changes on that. Yeah. When the jitter exceeds what the DSP can do to make up for the missing packet, audio problem are heard. Maybe we lost some conversation a little, yeah. But very little they try to do a correction there. Yeah. Okay, in properly notes, in a properly designed network, packet loss should be near to zero. So there's a challenge for this type of the application or algorithm. Okay. All right. Traffic characteristic.
Voice traffic and video traffic place a greater demand on the network and are two of the main reasons for QoS. There are some differences, though, between voice and video. Though they are both demanding, voice packets do not consume a lot of resources because they're not very large and they're fairly steady. So the characteristics are smooth and benign in regards to the demand it places on the network. However, voice traffic is sensitive to drops and delays and therefore requires prioritization. Packet loss should be no more than 1% with voice traffic. And voice traffic requires at least 30 kilobits per second of bandwidth. Now, video traffic is demanding. The size of the packets that it sends across the network are more bursty and more greedy. It consumes a lot more resources. It's also sensitive to drops and sensitive to delay, and it requires no more than 0.1 to 1% loss of packets and requires at least 384 kilobits per second in bandwidth. In this next graphic, you can see some of the differences. You can see that the audio samples of voice packets are fairly consistent at 20 milliseconds per sample, and the size of the packets are very small. However, video packets, depending on the frame of video, if there's nothing changing in a frame, then they might not have a lot of size. But if there's a lot of action, let's say in the video or in the movie, then the frames are going to be very greedy or very large. So you can see that it places a greater demand on the network. Data traffic is different from voice and video traffic in that it's generally not as demanding. Also, a lot of data traffic is sent with TCP applications, which can retransmit and are therefore insensitive to drops and delays. There are different types of data traffic. There is mission-critical data traffic and non-mission critical data traffic, interactive traffic and non-interactive traffic. If you have interactive mission-critical traffic, like in bank transactions or purchases, then there is the expectation of a quick response time in the data. However, a lot of traffic is not interactive and not mission critical, let's say a standard web page, and can therefore be the least prioritized.
All right. So regarding the voice, video, and traffic data. Okay, network traffic trends. In the early 2000, yeah, the predominant types of IP traffic were voice and also data. So voice traffic has predictable bandwidth need and known packet arrival times. Data traffic is not it's not real time and has unpredictable bandwidth needs. Data traffic can temporarily burst as when a large file is being downloaded. This bursting can consume the entire bandwidth of a link. More recently, video traffic has become increasingly important to business communication and also operation. According to the Cisco Visual Networking Index, VNI, video traffic represented 70% of all traffic in the year 2017. By 2012, video will represent 82% of all traffics. Mobile video traffic will reach to 60.9 exabytes per month by 2022. The type of demand such as video, voice, video, and data traffic placed on the network are very different. Voice traffic is predictable and smooth and very sensitive to delay and also drop packet. Okay, voice, very important. Voice packet must receive a higher priority than other type of traffic. Okay, so in Cisco product use RTP port range 16, 1384 to 32,767 to prioritize voice traffic. Okay, voice can tolerate a certain amount of latency, jitter, and loss without any noticeable effect. Okay, very low, nearly to zero. Okay, for the voice, latency should be no more than 150 milliseconds. Jitter should be no more than 30 milliseconds, and packet loss no more than 1%. Voice traffic require at least 30 kilobit per second of bandwidth. Okay, so voice traffic characteristic. First, we have a look for this: smooth, benign, drop sensitive, delay sensitive, also UPD priority. So requirement all this, as you can see on the previous one here, and also you can see in here. All right. Okay. So video traffic tends to be unpredictable, inconsistent, and bursty. Compared to voice, video is less resilient to loss and has a higher value of data per packet. The number and size of video packet varies every 30 milliseconds based on the content of the video. UDP ports such as 554 are used for RSTP or real-time stream protocol and should be given priority over other, less delay sensitive and also network traffic. Latency should be no more than 400 millisecond. This one. And jitter should be no more than millisecond. All right. And then the video packet loss should be no more than 1%. And also video traffic require at least 384 kilobit per second of bandwidth. So characteristic of the video, you can see like they use a word bursty, greedy, drop sensitive, delay sensitive, and also UPD priority. Okay, some priority on the data characteristic, especially on video. All right, data. So data application that have no tolerance, for data loss, such as what? Email, web pages. Okay, use TCP to ensure that if packets are lost in transit, they will be resent. Data traffic can be smooth or bursty. Network control traffic is usually smooth and predictable. Some TCP application can consume a large portion of network capacity. FTP, file transfer protocol, will consume as much bandwidth as it can get when you download a large file, such as movie or game. Yeah. So this, I can say, is a high volume of the data compared to others. Okay, data traffic characteristics. Again, we have voice and data. Sorry, video and voice, smooth, bursty, benign, greedy, drop, insensitive, delay, insensitive, and TCP retransmit. Yeah. So data traffic is relatively insensitive to drop. So back the fundamental idea, insensitive to drop and delay compared to voice and video. Yeah. Quality of experience, QoE, is important to consider with data traffic. Does the data come from an interactive application? So of course they will look for this. Okay, interaction. So we have to put priority on this. So very important. Is the data mission critical? Also, we need to see that. Okay, so maybe we relate to the medical, during the the real time surgery whatsoever. So you have to look for this is data mission critical. Sometime during that kind of the works we need more accurate. So this is quality we have to look. That's why right now, if you can see, okay, in ISP they divided, especially when we go for the general, right, general term like end user right now, especially games. Games right now they're using a lot of bandwidth and value. So they put higher pay on that, higher pay, especially for the fees as well, because they need to handle about this issue, quality of experience. Okay, when we're using a game, so we need a lot of bandwidth, so loss, not latency, lagging is very important. So if it lags, even we have a good machine, okay, but so now most of them ISP they try to aggregate all this the user experience. Okay. So factor, okay, they look for factor, interactive or non-interactive. Okay, if interactive, they should give a more higher priority. So mission critical, okay, prioritize for the lowest delay for all data traffic. And for also very important. Okay, not mission critical application should be a lower delay. Right. So delay can be for non-interactive. Okay, delay can vary greatly as long as the necessary minimum bandwidth is supplied. And so for the non-mission, for interactive, any level of bandwidth after all voice, video, and other data application needs are. Okay, so them, especially in they look for sometimes we're using a cable, but even for this, we call this the 5G. Okay, so they look for this issue also, how they can improve according to this quality of experience, right? Okay, keep rhythm. So let me play again. Video for QL. All right, okay.
If we look at the queuing strategies for QoS, FIFO queue, or first in, first out queuing, is basically the absence of QoS. In other words, packets that enter the router leave the router in the same order. Compared with QoS and weighted fair queuing, or WFQ, and packets that come into a router, let's say, are then classified and prioritized based on the classification. So high classification packets are prioritized when they're sent out of the router. A newer form form of weighted fair queuing is class-based weighted fair queuing, where specific classes of traffic can be configured by the administrator and used to prioritize different types of traffic. In order to guarantee that voice traffic is prioritized to the point where it ops, low latency queuing can be used with class-based weighted fair queuing to prioritize voice packets above all else, ensuring that voice calls will not drop off. The example you see here, a combination of low latency queuing, a priority queue, in combination with class-based weighted fair queuing to achieve that very result.
All right. Okay. So that's regarding the couple of quality of service algorithm. Okay, the quality of service policy, yeah, implemented by the network administrator become active when congestion occur on the link. Queuing is a congestion management tool that can buffer, prioritize, and if required, the packet before the destination. A number of queuing algorithms are available here. You can see 54 WFQ, CBWFQ, and also LLQ. So this is the queuing algorithm existing. Yeah. All right. First in, first out. First in, first out queuing buffer and port packet in the order of their arrival. Okay. 54 has no concept of priority or classes of traffic and consequently makes no decision about packet priority. Okay. All right. So there is only one queue for all packet are treated equally. Okay. And packet are sent out and interface in the order in which they arrive. Okay, weighted fair queue. Yeah, queuing, WFQ. Weighted fair queuing or WFQ is an automated scheduling method that provides fair bandwidth allocation to all network traffic. Right? WFQ apply priority. Okay, there is a priority or weight. Yeah, to identify traffic into conversation or flows, and then determine how much bandwidth and each flow is allowed relative to other flow. Okay, and then WFQ classify traffic into different flow based on source and destination IP addresses. Okay, MAC addresses, port number, protocol, and type of services value. WFQ not supported with tunneling and encryption because these features modify the packet content and information required by WFQ for classification. Okay, this is some criteria, okay, or some requirement order for them to process all the data. All right. Okay. So class extends the standard. Okay, extend the standard or enhance the standard of WFQ and then goes to this class base ability to provide the defined traffic classes. So traffic classes are defined based on match criteria, including protocols, access control list, AL, and input interfaces. Okay, packet satisfying the match criteria for a class constitute the traffic. A FIFO queuing queue is reserved for each class, and traffic belonging to it is directed to the queue for that class. The class can be assigned characteristics such as bandwidth, weight, and also maximum packet limit. Yeah, the bandwidth assigned to a class is the guaranteed bandwidth delivered during conditions. Packet belonging to a class are subject to the bandwidth and queue limits, which is the maximum number of packets allowed to accumulate in the queue that characterize the class. Okay, so this is some issue with the CBWFQ stand WFQ. Okay, after a queue has reached its configured queue limit, okay, adding more packet to the class causes a tail drop or packet drop to detect effect, depending on how class policy is configured. Okay? So tail drop discards any packet that arrive at the tail end of a queue that has completely up its packet holding resources. This is the default queuing response to congestion. Yeah? Tail drop treats all traffic equally and does not differentiate between classes of service. Okay, so they treat all equally. At the beginning, yes, they classify, but here they treat equally. LL low latency. Yeah, LLQ feature bring strict priority queuing PQ. Yeah, strict priority queuing CBWFQ. Okay, LLQ. So strict PQ or strict priority queuing allow delay sensitive packets such as voice to be sent before packet in other queue. All right. So LLQ allow delay sensitive packets such as voice to be sent first before packet in other queue. Okay. And this giving a delay sensitive packet preferential treatment over other traffic. Cisco recommends that only voice traffic be directed to the priority queue. Okay, so Cisco recommend that only voice traffic be directed to the priority queue. So now we go for model of quality of service. Okay, come back to here, look for some video. Where is the, all right, some video. We miss things. Oh, we lost. Okay, 1 second.
In a very general understanding of QoS mechanisms, let's first look at the QoS models. The best effort In a very general understanding of QoS mechanisms, let's first look at the QoS models. The best effort model is not really an implementation of QoS, as packets are delivered on a best effort basis, and QoS is not really required or configured. The integrated services model, or INT serve model, provides a very high degree of QoS to IP packets with guaranteed delivery. It uses a signaling process known as RSVP, or Resource Reservation Protocol. The INT-serve model can severely limit the scalability of a network, and it is demanding on resources and therefore doesn't scale well for large or enterprise networks. The differentiated services model, or DiffServ model, is a highly scalable and flexible implementation of QoS. It works off of manually configured traffic classes, which need to be configured on routers throughout the network. If we look at some of the benefits and drawbacks of the best effort model, you can see that under benefits, no special QoS mechanisms are required, and it is the easiest and quickest model to deploy. However, under drawbacks, notice that there are no guarantees of packet delivery. No packets have preferential treatment, and critical data is treated the same as casual email is treated. Basically, this is a non-QoS solution. Now compare this to the integrated services model, looking at some of the benefits and drawbacks. Under benefits, you can see that the INT model has tighter QoS for real-time traffic, uses the signaling protocol RSVP, Resource Reservation Protocol. It requires end-to-end signaling and per request admission control. It uses packet classification, policing, queuing, and scheduling. Under drawbacks, notice that the INT flow-based approach is not scalable to large implementations such as the internet, and the integrated services model is rarely deployed by itself alone. Looking at this diagram, we can see that end-to-end signaling is required in the integrated services model. RSVP is implemented on the routers within the network and can be implemented on the hosts as well. Notice the QoS-aware nodes. Sessions and resources are dynamically reserved one flow at a time. Now, looking at the differentiated services model, we can see some of the benefits and drawbacks. Under benefits, the differentiated services model provides better QoS scalability. It is a defined class-based approach, defining the policy and priority at the routers, known as per hop behavior, or PHB. It uses packet marking directly in the packets. In other words, packets are marked at the routers. It can also use NBAR or NBAR2 network-based application recognition services. It uses the 6-bit differentiated services code point, or DSCP, in the IP header, and is also used with IPv6. Under drawbacks, it doesn't provide the absolute guarantee of service that integrated services does, and it requires a set of complex mechanisms to work throughout the network. This is why differentiated services is often used with integrated services. Both the integrated services and the differentiated services models are not exclusive, and they can be used together. In this diagram of the differentiated services example, you can see that the QoS nodes are unaware that QoS is being implemented across the network. That's because a manual QoS policy has been configured on the routers in the network. Notice that as traffic goes across the network, the traffic is classified and colored.
All right. Okay. So that's regarding a model of quality of service. Okay, selecting an appropriate quality of service policy model. There are three different model for implementing quality of service or QoS. QoS is implemented in a network, either in-serve or diff-serve. Yeah, in-serve provide a high guarantee of quality of service. It is very very resource intensive, and therefore not easily scalable. So there's they can achieve some. Let's say this one is very resource intensive, but not easily scalable. Okay, so some parameter they need to sacrifice all this. Okay, this is quite challenge about in quality of service. Okay. So some parameter they need to sacrifice, some not. So that's why there's a lot of depend on that type of application. While diff-serve is less resource intensive and more scalable. Okay, all right. And in-serve and diff-serve are sometimes co-deployed in network quality of service implementation. So model, we have the best effort model, okay, and integrated services, the one that we mentioned just now, and also differentiated services or diff-serve. For the best model, for the best model, not an implementation as quality of service, not explicitly configured. Okay, use when quality of service is not required. For the in-serve, for the integrated services, provide very high quality of service to IP packet with guarantee delivery. Define a signaling process for application to signal to the network that they require special quality of service for a period that bandwidth should be reserved. Yeah. INSERV can severely limit the scalability of a network. Okay, there's some limitation for these integrated services, yeah. And differentiated, yeah, services or DiffServe provide high scalability and flexibility in implementing quality of service. Network devices, yeah, recognize traffic classes and provide different level of quality of service to different traffic classes. Best effort. The basic design of the internet is a best effort packet delivery and provide no guarantees. Okay, that's for internet. Yeah. So the best effort model treats all network packet in the same way. So an emergency voice message is treated the same way that a digital photo graph attached to an email is treated. Okay, same. Yeah, no difference. Benefit and drawback for of the best effort model. So benefit model is the most scalable. Okay, and then there's no guarantee of delivery. All right, and then scalable is not limited by available bandwidth, in which case all traffic is equally affected. Okay, for the drawback, packet will arrive whenever they can, and in any order possible. Okay, if they arrive at all, and then no special quality of service mechanism are required. And for the drawback for this is no packet have preferential treatment. Okay, they equally yeah they will treat. It is the easiest, yeah, and quickest model to deploy for the best effort. But critical data is treated the same as casual email is treated. Okay. So integrated services, INSERV, okay, deliver the end-to-end quality of service that real-time application required. So based on the application. Some application they prefer to have these integrated services, some not. Okay. So explicitly, yeah, manage network resources to provide quality of service to individual flows or streams, sometimes called micro flows. Yeah. Use resource reservation and admissions control mechanism as a building blocks to establish and maintain quality of service. Use a connection-oriented approach. Yeah, each individual communication must explicitly specify its traffic descriptor and requested resources to the network. The edge router perform admission control to ensure that available resources are sufficient in the network. All right. Okay, this one more on specific that require this integrated service. So in the in-serve model, yeah, again in the integrated services, the application requires a specific kind of service from the network before sending a data. For example, the application inform the network of its traffic profile and request a particular kind of service that can encompass its bandwidth and delay requirement. And also, INSERV use the resource reservation protocol, yeah, to signal the quality of service needs of an application traffic along devices in the end-to-end path through the network. If network devices, yeah, if the network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails along the path, the originating application does not send any data. Okay, so this one is the benefit of integrated services and some drawback stated in here, right? Okay, differentiated services. The differentiated services or DiffServe quality of service model specify a simple and scalable mechanism compared to the previous one, which is integrated services. Yeah. So especially for classifying and also managing the network traffic. Yeah. It is not end-to-end quality of service strategy because it cannot enforce end-to-end guarantee. Post forward traffic to a router, yeah, which classify the flow into aggregates So classes, yeah, into the aggregates and also classes, and provide the appropriate quality of service policy for the classes. And next, enforce and apply quality of service mechanism on a hope by hope basis, uniformly applying global meaning to each traffic class to provide both flexibility and also scalability. Okay. They also provide a network traffic into classes based on business requirement. Each of the classes can then be assigned to a different level of service. As the packet travels a network, each of the network devices identify the packet class and services the packet according to that class. It is possible to choose many levels of service with diffserv. Yeah. And benefits are high scalable, okay, and also provide many different level of quality. And for the weaknesses or drawbacks, you can see no absolute guarantee of service quality and require a set of complex mechanisms to work in concert throughout the network. Quality of service implementation techniques. All right. Quality of service, yeah, implementation technique.
We can categorize QoS implementation tools into three broad categories: classification and marking tools, congestion avoidance tools, and congestion management tools. Under classification and marking tools, session traffic is classified into different priority groupings and packets are marked. Under congestion avoidance tools, traffic classes are allotted network resources. Some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Weighted random early detection regulates TCP data traffic in a bandwidth efficient manner before tail drops caused by queue overflows, basically congestion, occurs. And under congestion management tools, when traffic exceeds available network resources or we have congestion, then traffic is queued to await the availability of those resources. Common Cisco iOS-based congestion management tools include class-based weighted fair queuing and low latency queuing, or the CBWFQ and LLQ algorithms. If we look at this diagram, you can see the three segments to the egress or exit interface of the router. You can see that traffic is first classified and then marked. Notice in the graphic how the packets before being classified are all seen here as gray. As they're classified in different classes, they're marked in the IP header, indicated here with the colorization of the different packets. Congestion avoidance is where traffic is policed and selectively dropped. This is where network resources are allotted into different priorities. Packets are put into different queues based on different weights or sizes. The main congestion avoidance tool that's used in Cisco devices is weighted random early detection, or W. If queue buffers fill up, packets may be dropped proactively as to avoid congestion. Lastly, we have the congestion management section where packets are put into their queues and are scheduled and shaped based on the network priorities or policies that have been applied. If we look a little closer at QoS traffic marking, we can see that traffic marking happens at both layer 2 and layer 3. At layer 2, we have class of service, or CoS, which happens using the 802.1q VLAN tagging and 802.1p quality of service protocols. Traffic marking at layer 2 happens on the local area network and is limited to the LAN using layer 2 switches. Under Wi-Fi, traffic marking happens with the Wi-Fi Traffic Identifier Field, or TID. With MPLS, you have the Experimental, or EXP field, also at layer 2. At layer 3, with IPv4 and IPv6, we use the ToS and traffic class fields using IP precedence, or IP, and DSCP, differentiated services code point. With layer 3 traffic marking, the marking can go from router to router, and therefore the QoS marking can be carried end to end across the network. In this slide, you can see how QoS marking happens at layer 2. We have an Ethernet frame, and the 802.1q protocol can be inserted between the source address and the type length field. You can see the two fields inserted into the Ethernet frame, the TPID field and the TCI field, or Tag Control Information field, which contains a 3-bit PRI priority field, which identifies the class of service, or COS marking. The class of service markings have 6 different values: best effort, medium priority data, high priority data, call signaling, video conferencing, and voice bearer for voice traffic. Bits 6 and 7 are reserved for network control information. At layer 3, QoS is implemented in the IPv4 and IPv6 packet headers in the type of service field and the traffic class field. In the older implementation, class of service at layer 3 was implemented using IPP and ToS. The IP precedence is 3 bits, and the type of service is 5 bits, and you can see them there in the 8 bits. The classifications have 8 levels, which map to layer 2 class of service. You can see there routine, priority, immediate flash, flash override, and critical. Once again, values 6 and 7 are reserved for network control information. The current implementation of QoS uses the differentiated services code point and explicit congestion notification fields, or DSCP and ECN. DSCP and ECN map directly over the 8 bits of the IPP and ToS fields, and the DSCP field is backwards compatible with the IPP field. You can see in this example that an IPP classification of 5 involves the 1 here and the 1 here. If you have IPP and you have 3 bits, then this would be a 4 and a 1, which would be a 5, which would signal a critical flow. Under the DSCP specification, you have 6 bits. It's 1, 2, 3, and this is a 32, and this is an 8, and 32 plus 8 is 40. So you can see how it would map under IPP using 3 bits, or a 40 using DSCP using 6 bits. Since DSCP uses 6 bits, there are 64 possible classifications of traffic. QoS marking happens at trust boundaries, and marking should happen as close to the source as possible. Endpoints like voice over IP phones, wireless access points, and video conferencing gateways have the ability to mark QoS packets, as indicated in number 1. Traffic can also be marked using layer 2 switches, as in number 2, or at layer 3 using layer 3 switches and routers. As packets travel across the network, the remarking of the traffic can be necessary. The remarking of class of service values, or IP precedent values, or DSCP values. The main mechanism of congestion avoidance in QoS on Cisco routers and switches is weighted random early detection, or WRED. With weighted random early detection, a percentage of packets are dropped once we've gone over in a queue the minimum threshold. If the queue has gone over the maximum threshold, then packets are automatically dropped. In this image, you can see the difference between traffic policing and traffic shaping. In traffic policing, when the traffic rate reaches the configured maximum rate, excess traffic is dropped. The result is an output rate that appears as a sawtooth with crests and troughs, as shown in the graph at the top. With traffic shaping, excess packets are retained in a queue and then rescheduled for later transmission over increments of time. The result of traffic shaping is a smooth packet output rate, as shown in the bottom graph.
All right. Okay, so that's the implementation techniques on quality of service. Avoiding packet loss. Yeah? Packet loss is usually the result of a congestion on interface. Yeah? Most applications that use TCP experience a slowdown, yeah, because TCP automatically adjusts the network congestion. Drop TCP segment cause TCP session to reduce their window size. Some applications do not use TCP and cannot handle drops. Yeah, and the following drops in sensitive application increase link capacity to ease or prevent congestion, guaranteed enough bandwidth, and increase buffer space to accommodate bursts of traffic fragile flows, WFQ, CB, WFQ, and also LLQ. All these algorithm in queuing algorithm can guarantee bandwidth, yeah, and provide prioritized forwarding to drop sensitive applications. Drop a lower priority packet before congestion occur. Okay, so this is Cisco. Cisco IOS quality of service provide queuing mechanisms such as weighted random early detection or WRED that start dropping lower priority packet before congestion occur. Okay, they do some add-on on this, which is they call the WRED. So they start drop packet before congestion starts. Okay, quality of service tools. There are three categories of quality of service tool. Okay, you can see here. So classification and marking tools. Okay, these actually session or flows are analyzed to determine what traffic class they belong to. And when the traffic is determined, the packet are marks. Okay, and another category. So first to congestion avoidance a tool. Okay, so these two actually traffic classes, yeah, are allotted a portion of network resources such as defined by the quality of service policy. And the quality of service policy also define how some traffic may be selectively, yeah, drop, delay, and also remark to avoid congestions. The primary congestion avoidance tool, which is WRED, and is used to regulate TCP data traffic in a bandwidth efficient manner before caused by queue overflows occur. Yeah. And another category, congestion management tools. When traffic exceeds, yeah, available network resources, yeah, when the traffic exceeds available network resources, traffic is queued to await availability of resources. So common Cisco iOS based congestion management tool include CBWFQ and also LLQ algorithm. All right. So these are the quality of service tool, yeah, categories. And then the figure shows the sequence of quality of service tools when used when applied to a packet flow. Okay, you have seen this in the video recently. So actually the English packet are classified and their respective IP header is marked. Yeah. And then to avoid congestion, yeah, packet are then allocated resources based on defined policy. Packet are then queued and forwarded out the English interface based on their defined quality of service shaping, and also according to the uh, policy. Yeah, policy. On a note, classification and marking can be done on ingress or ingress, yeah. Whereas other quality of service actions such as shaping are usually done on ingress. Classification and also marking. Before a packet can have a quality of service policy applied to it, the packet has to be classified. Okay, they do aggregation. So classification determines the class or of traffic to which packet or frame belong. Only after traffic is marked, then can policy be applied on it. So they do classification, or what we call here, they said aggregate the packet, and after that the policy can be applied on it. Yeah. How a packet is classified depend on the quality of service implementation. Method of classifying traffic flow at layer 2 and 3 include using interfaces, ACL, and also class map. Traffic can be classified at layer 4 and 7. Sorry, 4 7 using network-based application recognition. Okay, which is in the until a layer application layer. So this is the network application recognition, or NBAR. Yeah. Okay. So how traffic is marked usually depends on the technology. The decision of whether to mark traffic at layer 2 or 3 or even both is not trivial and should be made after consideration of the following point. First, layer 2 marking of RAM can perform for non-fake. Layer 2 marking of RAM is the only quality of service option available for switches that are not IP aware. Layer 3 marking will carry the quality of service information end to end. So it's a quality of service tool. We have Ethernet 802.1Q and also 802.1P. Yeah? So layer 2 class of service. So this one is already mentioned in the video. And for the quality of service tool for the Wi-Fi, we have layer 2 and then work at the 3 bits. So Wi-Fi traffic identifier, which is TID. Yeah, MPLS. Yeah, so layer 2 experimental. So which is they occupied for 3 bits, and for the IPv4 and IPv6, which is for monitoring and controlling network. So they use layer 3 and also layer 3 for this. And the width in bit is 3 bit for IPv and also for DHCP using 6 bit. Yeah. Right, marking at layer 2. 802.1Q is the IEEE standard that support VLAN tagging. Remember that? Yeah. This 802.1Q, yeah. Tagging at layer 2 on Ethernet networks. When 802.1Q is implemented, 2 fields are inserted into the Ethernet frame following the source MAC address. Okay, here is the one. From here they will add on. All right. Okay. So the 802.1Q standard also include the quality of service prioritization schemes such as IEEE 802.1P. The 802.1P standard, yeah, use the first 3 bits in the tech control information TCI, known as priority PRI field. This 3-bit field identify the class of service, quality of service marking. 3-bit means that a layer 2 Ethernet frame can be marked with one of 8 level of the priority, which is value 0 to 7. All right. So here is the detail of that. Okay. Marking at layer 3. IPv4 and IPv6 specify an 8-bit field in their packet to mark a packet. Both IPv4 and IPv6 version support an 8-bit field for marking. So the type of TOS field, yeah, TOS field and also for IPv4 and traffic class field for the IPv6. All right. Okay, this is the right. Yeah. So yeah. All right. Okay. So service and traffic class field. The type of service IPv4 and traffic class IPv6 carry the packet marking as assigned by quality of service classification tools. Yeah. Okay, RFC 791. Yeah, 791 specify a 3-bit IPv field to be used for quality of service marking. And RFC 2474 supersede RFC 791 and redefine that a ToS field by renaming and extending the IPv field to 6-bit. All right. And then call the differentiate services code point, DSCP field. This 6-bit offer a maximum to 64. Yeah, 6-bit means that 64 possible classes of services they can offer. Yeah, the remaining 2 IP extended congestion notification or ECN bits can be used by ECN aware router to mark packet instead of dropping. Okay, that's regarding type of service and also traffic class field. DSCP value. The 64 DSCP value are organized into 3 categories: best effort, expedited forwarding, and short forwarding. Yeah. So best effort, this is the default value for all IP packet. So the DSCP value is 0. Yeah. The per hop behavior is normal routing. When router experience congestion, this packet will be dropped. No quality of service plan is implemented. So expedited forwarding, yeah, this is the RFC standard. Yeah, define this, yeah, as the DSCP decimal value 46. Yeah, the first 3 bits 101 maps directly to the layer 2, and then QoS value 5 used for traffic, used for voice traffic. Recommend that the app only be used to mark a voice packet. Okay, more detail you can look for the RFC document 32324. 3246. Yeah. Ensure forwarding AF RFC 2597. Yeah, for this. So define AF to use a 5 most significant DSCP bits to indicate queue and also drop preference. Ensure forwarding value are shown in the figure. All right, in this figure. Okay, the AF XY formula is specified. So this is AF. Okay, this is F, X, and so Y here. Okay, the first 3 most significant bits are used to design the class. Okay, class 4 is the best queue, and class 1 is the worst queue. The 4th and 5th, yeah, most significant bits are used to design it, the drop preference. Yeah, and then the 6th most significant bit is set to 0, right? The class selector CS. The first 3 bits significant bit of the DSCP field and indicate the class. Map directly to the 3-bit of the QoS and the QoS field and the IPv field to maintain compatibility with 802.1p and also the RFC 791. Trust boundaries. Traffic classified and not as close to its source and technically and administratively feasible. Yeah, this define the trust boundary. Trusted endpoint have capabilities. Yeah, and intelligent to map application traffic to the appropriate layer 2 QoS and the layer 3 DSCP. Yeah. Second, secure endpoint can have a traffic mark at the layer 2 And the third one, traffic can also be marked at layer 3 switches or routers. Okay, here's the one. Yeah, you can see the close as to the user. They will start to do this. Okay, congestion avoidance. Congestion avoidance tool monitor network traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottleneck before congestion becomes a problem. They monitor traffic loads in an effort to anticipate and avoid congestion at common network and network bottleneck before congestion become a problem. Yeah, they monitor the average depth of the queue. When the queue is below minimum threshold, there are no as the queue fill up to the maximum threshold, a small percentage, yeah, of packet are dropped. All packets are dropped. Some congestion avoidance techniques provide preferential for which packet get dropped. So in WRED, yeah, WRED or weighted random early detection allow for congestion avoidance and network interfaces, yeah, by providing buffer and allowing CV traffic to decrease or throttle back before buffer are exhausted. WRED help avoid tail drops and maximize network use and TCP based application performance. Okay, so this is some good of this WRED. Yeah, shaping and policing. Traffic shaping and traffic policing are two mechanisms provided by Cisco IOS. Yeah. In terms of quality of service. Traffic shaping retain access packet in queue, then schedule the access for later retransmission over increment of time. Traffic shaping result in a smooth packet output rate. Yeah, shaping is an outbound concept. Packet going out and interface get queue and can be shaped. In contrast, policing is applied to inbound traffic on the interface. Yeah. So there from here, yeah, the original data, and then at the end they will generate this constant traffic. All right. So policing is apply. Yeah, policing. Yeah? Policing is applied to inbound traffic on an interface. Policing is a commonly implemented by service provider to enforce contractor customer information rate (CIR). However, the service provider may also allow bursting over the CIR if the service provider is not currently experiencing congestion. Okay, and this is how they do a policing. Yeah, if you look the original data, it's like this. The policing, they will keep on maintaining this. Quality of service policy guideline. Quality of service policies, yeah, must consider the full path from source to destination. A few guidelines that help ensure the best experience for end user include the following issue. First, enable queuing at every device in the path between source and destination. And secondly, classify and mark traffic as close to the source as possible. Okay. And third one, shape and polish. Yeah, polish traffic flows as close to their source as possible. Okay, so these are some guideline to improve the quality of service policies. All right. Okay, that's all for quality of service.